Hello, everyone. Thank you for coming to our symposium. My name is Xiao Yang. I'm currently a postdoc researcher in the Department of Psychology at Stanford University. Today, I will be talking about Boolean network method, which is a nice method to describe and control multivariate nonlinear dynamics. This is an overview of the Boolean network control method, and we used it to inform personalized intervention. We started with time series data or binary time series data from children's emotion regulation studies, and then used Boolean network to model the temporal dynamics between emotion and behavior. And eventually we want to derive what's the emotion landscape of a particular child, whether they're likely to be stuck in anger, and how to recommend behaviors so that we can move them out of anger state to a more neutral state. The innovation of this line of work is to introduce network control literature to psychology applications and then to inform personalized intervention using if-then rules, which is very easy to remember and practice. To give you an overview of the terminologies, a network usually has nodes and edges. In Boolean networks, the nodes are variables with binary states. For example, in emotion regulation studies, sometimes researchers record videos of participants, especially when they're children, and then they will manually code the emotions and behaviors using 0 or 1 codes. So that's where the binary time series is coming from. And the edges are temporal relations. In Boolean networks, the temporal relations are described by Boolean operators, which are and, or not, and the combinations of them. So for example, this is a Boolean function in part of the Boolean network. And here, anger at t plus 1 is predicted by anger at time t and not distraction at time t. And from the Boolean network, we can design network control, especially to find behavior modification strategies so that we can inform the individual or the parent or teacher how to modify behavior to move a person from an angry state to a more neutral state. So the innovation here is to use the Boolean functions to describe the temporal dynamics in a multivariate binary time series data, and then to design network control. In this empirical study, we design network control for self-regulation dynamics or emotion regulation dynamics during early childhood. The importance of self-regulation is that it contributes to children's later socio-emotional development, and it helps children focus on teacher-defined activities, especially they need to be able to wait when teacher is preoccupied with other children, or ask them to wait when teacher is finishing a task herself or himself. And there has been personalized intervention methods suggested and developed before, especially coming from the person-specific approach and dynamical system-based control design approach. And we wanted to complement this body of literature by providing Boolean network control, which has been used in gene regulatory networks, because it can handle the nonlinearity in the dynamical system. And very few methods previously have examined the nonlinear dynamics. Most of them focus on the linear dynamics. And we also want to provide this method as a modeling technique for child developmental studies, which often collect video data because self-reports is not very realistic for children to fill out. So video recording and manual codes, which is usually in the binary time series format, is a wealth of data that we haven't really examined the temporal dynamics of. So those are the two motivations we wanted to promote this method. So for the empirical data, it's a toddler study at 36 months. Half of them are boys with 120 participants. The children were given a gift-wrapped toy when they're brought into the lab, and they were instructed to wait to open the toy until their mother finishes the survey, which lasts 8 minutes. During those 8 minutes, there are emotions. You can imagine emotions and behaviors would emerge from the child, and the RAs manually coded second by second, what are the emotions and behaviors emerged given each second. And we selected 3 variables here to model the temporal dynamics, which are anger and bidding and distraction. And previous theory has suggested that bidding is more likely to make anger to persist, and distraction is more likely to make anger to be regulated. And here I'm showing you a data visualization of one child's data. The x-axis is time here, 480 seconds, and the colored bars indicate whenever the emotion or behavior is observed, and the white space indicate whenever the emotion and behavior is not observed. So coming from that binary time series, we can use Boolean network to construct for each child their person-specific Boolean networks. And the Boolean network consists of the Boolean functions to describe each variable's temporal dynamics. For example, here, for the 3 variables we selected, there are 3 Boolean functions. The first one is anger at t plus 1 is predicted by anger at time t, and not distraction at time t. And bidding and distraction are predicted by themselves from the previous time point. The technical level of this estimation is to find the closest match of the outcome variable using Boolean operators with input nodes. So for example, if we have one outcome variable, x1t plus 1, we have their observed time series here. And we can also construct input variables by combining different input variables and different Boolean operators, and we can enumerate them. And we can compute this form of Boolean function using the observed time series, because we know the time series of x1, x2, x3, and we can compute x1 and x2 at time t. And we have this time series for this function and this time series for this function. And then we compare the outcome variable time series with this Boolean function time series. And we found there are 2 digits at 2 different time points that are not equal to each other. And the number of mismatch is counted as error. So for this Boolean function form, there's an error of 2. And for this Boolean function, because they equal to each other at each time point, the error is 0. And after comparing all the Boolean functions, we can infer the Boolean function for this x1t plus 1 is this Boolean function because it has the minimal error. The second step is to extract the attractors and to find if the child is stuck in an anger zone. And the method is to use the estimated Boolean functions to derive this attractor, which I will tell you momentarily. And here I want to highlight attractor is a state where the system tends to stay. You can think of it as if it's the bottom of a bowl, and if you drop a marble, it will be attracted to the bottom. That's why it's called an attractor. In the dynamical system world, there are states of a system where the system tends to stay in. So that's what we call attractor in this context. And in this emotion regulation case, we defined that the desirable attractor is when anger is off, and desirable attractor is when anger is on. So the technical detail of extraction of attractors is to examine the state transition based on the estimated Boolean functions. For example, we take 2 Boolean functions here. We can enumerate all 4 possible initial conditions for anger and distraction. And based on the right-hand side of the Boolean functions, we can infer what's the state of anger and distraction during the next time point. And we will take an example here. For example, if the initial state is 1, 1, so anger is 1 and distraction is 1, we can compute based on the right-hand side of the equation what's the anger and distraction at time t plus 1. So let's do it for one case. So anger is 1, distraction is 1, and not distraction will be 0, and 1 and 0 will be 0. So anger at t plus 1 is 0 here, and distraction is simply predicted by itself directly, so it's 1. And then we can plot this state transition graph. So you can see 1, 1 here is transitioning to 0, 1. And whenever there is a state that transitions back to itself, we know it's an attractor, because once the system is in that state, it transitions back to itself, means it's staying in that state. And here, the undesirable attractors are these 2 because anger is 0, and the desirable attractor. The undesirable attractor is this one because anger is 1. The third step, after we have the attractors derived, we can design network control if it's needed. So we want to find a behavior modification so that we can move the child out of the anger zone. And we developed a search algorithm to find the shortest distance from undesirable attractor to desirable attractor basin. And the control strategy will look like this. If anger is on, then turn distraction on. And this turn distraction on is the behavior modification I was referring to. And the conceptual landscape will look like this. The child is stuck in anger, and by turning distraction on, we can move the child out of this attractor and move it into a more desirable attractor. And this network control design can inform parents or teachers about how to improve a child's self-regulation. On the technical level, this is done by computing the Hamming distance from undesirable attractor to desirable attractor basin and find the shortest distance that indicate the node to flip. So in this table here, this row is the undesirable attractor state, 1, 0. The 3 columns indicate the states in the desirable attractor basin, which are those 3 nodes or 3 states. And we can compute the Hamming distance here. For example, from 1, 0 to 1, 1, there is a distance of 1 because we only need to change this 1 node. And but we don't consider this a possible control design because the first digit represents anger. If we can manipulate anger that easily, there is no need to design a network control or behavior modification. So that's because changing emotion is often considered very difficult, and we need engage with some behavior to be able to regulate emotion. So this orange line here is not considered the behavior modification strategy. What we want is here, when anger is on, we turn distraction on, the second digit, and then the system will move to this desirable state, which anger is off and distraction is on. So the control strategy here is represented as this. This is the context of one control strategy is needed. This is the behavior modification of how to control the system. So this is a person-specific result to highlight that each kid or each child will get their own person-specific Boolean network estimated, their own state transition graph derived from the Boolean networks, and their own network control strategy. And you can imagine different child would have different control strategies, and this is exactly what we found when we scale up to the sample level. So for roughly a quarter of the child, there's clear difference in the desirability of attractors, just like the case we were showing you before, and we can identify behavior modification as control strategy. For a third of the sample, anger is mostly off, so children's anger is not elicited or rarely elicited from this experimental paradigm. They're well regulated by themselves at this age already, so there is no need of control. And for the rest of the sample, there's no simple behavior modification we could find as a control strategy. And we think this is the sequence when children develop their emotion regulation skills. And we are currently writing a longitudinal version of this Boolean network method using the same sample, same experimental paradigm from 2 to 5 year old. This paper alone is 3-year-old. So we're discovering longitudinally whether this is indeed the developmental sequence. So that's all of the method I want to show you. I want to reiterate, this is the steps that we engaged with to design network control to inform personalized intervention. First, we have binary time series data. Then we estimate the Boolean networks to describe the temporal dynamics in this time series, and then design network control to provide behavior modification strategy or if-then rules to inform how to intervene to improve self-regulation. And I want to give a shout out to my funding agencies, NIA and NSF, for funding my grad school work. And currently I'm at Stanford, and the Stanford Media Act funds my current development, especially this extension to the longitudinal Boolean network work. And I want to give a shout out to my collaborators at Stanford, Penn State, and various institutions. Thank you all very much for your attention. And if you're interested in reading more about the details of this method, and our tutorial, you can scan this code. That's the link to my website. Thank you very much.